Guess who? We have one more to complete this set. I hope it's one more. Now, I was talking about complexity, and basically I was talking about time complexity. How much time does an algorithm take? We always have to have a measurement of the size of the input. It might be the number of digits in the input. That's a pretty common one. We also need a measurement of the time. We want to count something. We usually count whatever takes the most time, like multiplications instead of additions. But we can count anything and get a rough idea of what's going on. Now, in this first example I did last time, I talked about adding two numbers with n digits. And it came out that we need 2 times n minus 1 plus 1 adds. Now you might say, well, what is that? What do we say about that? What about the 2 and the 1? Are they important? The answer is no. The order of an algorithm is the the order of an algorithm that runs in polynomial time is order the largest power. So addition is order n. Again, it is a linear algorithm. Now in reality, if it were 10 million n, we might have a little trouble with it when we get n pretty high. But still, it scales only linearly. It's a decent, good algorithm. Let's take another one. I think most of you know what a prime number is. It is a number that is only divisible by itself and by 1. How do we tell if a number is prime? Well, one of the oldest and crudest ways to do it is we can determine if a number is prime by dividing it by all integers less than or equal to the square root of the number. This algorithm rose as the square root of the input, of the magnitude of the input. That's probably a little better than the other one we have. And it's a trackable algorithm. There are ways to improve this, but I'm just going brute force here. Now let's consider another algorithm. Suppose suppose we are looking up a name in a telephone book. I know you don't have telephone books that much, but imagine we're living in the 50s or something like that. Now, the way you might do it is you go halfway in and you see if at the halfway you should go to the front or to the rear to find the name you want. This is the algorithm is a form of binary search. We can do it because we must have an ordered list, and the telephone book is ordered. Now, the first thing we do is compare what we want to find with the middle of the list. If it's there, great. We are done. If not, we have cut our work in half. Either the name is in either the first part of the list, or it is in the second part. And so we repeat what we did. Now we look at the middle of whichever half. Whichever half. Every time we make a comparison, we cut the list in half. So, if the list has, say, 8 elements, one comparison gives us 4 to look at. The second comparison gives us 2 to look at. And the final comparison gives us 1. So we get down to 1. And really the way we're doing this is the number depends on X, where the number of elements in the list is 2 to the X. This X is the log to base 2 of n. Now the order now is order log n. This is a better algorithm than a linear algorithm. To give you some idea of it, I went to my trusty Excel. I put a few in to see what I would get. And here's a few cases of n and log n. You'll notice even at 10,000, we're only talking about 13 comparisons or so. That's pretty good. That's much better than if we had a function of 10,000, a linear function. So an order log n algorithm is a fairly good algorithm. We like that. Now, not all algorithms are very good algorithms. Here's a very simple problem. Write out the multiplication table for n by n of size n by n. So for 3, we would get, and again I have this off here so that I don't have to think about putting it in. Give me a second. And this is what we would get. Now, we need to do n times n multiplications to get the numbers for this table. This is an order n squared algorithm. We basically like algorithms that have a polynomial bound. Those are good algorithms. And it can get worse, unfortunately. Let's try a very simple problem. Suppose you want to print out all the n-digit strings of zeros and ones. Computer speaks in terms of zeros and ones. We'd like to see how many things it can say in n digits. Now, there are 2 digits, 2, 0, and 1. So, for n equals 1, we have 2 strings, 0 and 1. For n equal 3, we have we have 8 strings. For n, this algorithm has order 2 to the n. It is exponential and not good. I'm out of time again. Well, I think you'll get the idea. I've got to stop. So I'll see you again soon, probably tomorrow. Bye now.